the analysis of domainwall encoding effect on Ising machine. This presentation is based on this paper were published on arXiv yesterday. This is the overview. In previous study, the domainwall encoding only has been proposed on one of the binary integer encodings. And in this study, we evaluated the performance of the domainwall encoding in the digital Ising machine using quadratic knapsack problem QKP. This study revealed that the performance of domainwall encodings improved with the ratio of the penalty coefficients between the two constraint terms. Second, the penalty coefficients for the total constraint terms that obtain feasible solutions was small in the domainwall encoding. Third, the domainwall encoding was highly sensitive to computation time. Let's move on the introduction. Ising machines are expected as efficient solvers for combinatorial optimization problem. This is a flow to search for the optimal solution by Ising machine. To tackle a combinatorial optimization problem on an Ising machine, the objective function and constraints have to be mapped onto QUBO. This is the Hamiltonian of QUBO, and xi is the binary variables. Binary integer encodings is a transformation that represents integer values using binary variables. Since the QUBO consists of binary variables, the value has to be encoded using binary variables when combinatorial optimization problem involve integer variables. This is major binary integer encoding. In one encoding, k variables express one-hot encoding needs k variables to express k integers. The way of the expression is the position where the binary variables takes one, as described in this figure. Binary encodings express the integer in binary form, so the number of variable requires is log base 2 of k. The domainwall encodings has been proposed in 2019 by Professor Kassler, and this encoding is k-1 variables, and this encoding is expressed by the position of the boundary between 1 and 0. Various previous studies evaluated the performance of binary integer encoding. In a previous study, the experiments using a quantum-annealing machine have shown that the domainwall encoding outperforms that of one-hot encoding in terms of the cost function and the probability of obtaining feasible solutions. However, because the QA machine has hardware restrictions, such as the interaction density and the number of variables that can be input, the evaluation of the inherent performance of the domainwall encoding was insufficient. And the condition to optimize the performance of the domainwall encoding were not investigated. In another previous study, the experimental results using the digital Ising machine have revealed that performance varies depends on the binary integer encoding. Here, digital Ising machines are implemented in digital circuit. These machines mitigated hardware restrictions compared to QA machines. However, the performance of the domainwall encoding was not evaluated on digital Ising machines. From the limitation of previous study, in this study, we evaluated the performance of the domainwall encoding in the digital Ising machine, and we explored the condition that improve the performance of domainwall encoding. I use QKP as one of the combinatorial optimization problem. This problem is aimed at maximizing the total profit of items packed into the knapsack without exceeding the knapsack capacity. This is the QUBO model of QKP. This QUBO consists of the objective function and constraint terms. And the constraint terms consist of the encoding constraint and weight constraint. Encoding constraints enforce the expression of integer, and weight constraints enforce that the weight of items which packed in knapsack does not exceed the knapsack capacity. This QUBO has two penalty coefficients. The mu controls the constraint terms, and lambda controls the encoding constraints and weight constraint relativity. Typically, the lambda was set to 0.5. In other words, the encoding constraints and weight constraints were the same. The objective function and constraint terms of one-hot encoding and domain-wall encoding as described as follows. I used first I evaluated the dependency of penalty coefficients and lambda. We use the QKP with 100 items and a knapsack capacity of 669 and 2360 and 66. There are the one spin difference between the one-hot encoding and domain-wall encoding I described before, and the interaction density is 25%, and a fixed amplifier in an annealing engine, which implemented simulated-annealing-based algorithm, was used as Ising machines. The computation time was set to 10 seconds, and penalty coefficients lambda was set to 0.01 to 0.99, which means that there are maximum 100 times difference from encoding constraints and weight constraints. The number of variables was set to 100. We evaluate the performance by evaluating these metrics. One is the feasible solution rate. Feasible solution rate is the performance of the feasible solution. Probability of feasible solution, which is among the total solutions. The feasible solution were defined as that solution satisfy the both encoding constraints and weight constraints. The optimality gap consists of the Hamiltonian of objective function of optimal solution and feasible solution. If the optimality gap is 1, the feasible solution is the optimal solution. This is the result. The left is the result of middle size QKP, and right is the large size QKP. The bottom and the top of the figure is the result of shows the feasible solution rate, and bottom shows the optimality gap. These metrics are also good if these metrics show higher value. The horizontal axis shows the lambda, and black denotes one-hot encoding, and red denotes domain-wall encoding. According to these figures, the domain-wall encoding performed better when lambda is greater than 0.5 compared to the commonly used condition of lambda equal to 0.5. When the number of variables is large, the domain-wall encoding obtains solutions with a higher optimality gap compared to the one-hot encoding. In the one-hot encoding, also the number of contained feasible solution is small. This solution indicates high optimality gap. However, practically it is assumed that the condition with high feasible solution rate and high optimality gap are preferable. Consequently, a new evaluation metric was devised. This is the feasible solution rate multiplied by optimality gap. These are results. These figures show that in metric concerning practical use, the domain wall encoding exhibits the higher values than the one-hot encoding in region when lambda is large. Next, we conduct a comparison of the practical evaluation metrics in program with multiple knapsack capacities. This table shows the knapsack capacity and the number of variables of one-hot encoding and domain-wall encoding, and there are the maximum value of feasible solution rate multiplied optimality gap and the corresponding lambda at that time. This figure shows the and blue shows a higher value than other encoding. According to this table, in program with a large number of variables, the domain-wall encoding significantly outperforms. In addition, the maximum value are obtained when lambda is greater than 0.9. Next, we evaluate the performance by a dependency of penalty coefficients mu. The penalty coefficients mu was set to 1, 10, 100. This is the result. The left is the result of one-hot encoding, and right is the result of domain-wall encoding. And these plots denotes each mu. With increase of the mu, the feasible solution rate increase and the optimality gap decrease in each encodings. However, the domain-wall encoding obtained the feasible solutions even with smaller mu, which means the mu equal 1 compared to the one-hot encoding. Next, I evaluate the performance by sensitivity to computation time. The computation time was set to 1 to 100 seconds. This is the results, and the blue denotes the result of 1 second, and magenta shows 100 seconds. With increase of computation time, feasible solution rate and optimality gap increase in both encodings, but in domain-wall encoding, the influence of computation time is more significant in the domain-wall encoding. So the domain-wall encoding is highly sensitive to computation time. To analyze the results, we investigated the dynamical process. We compared the dynamical process of one-hot encoding and domain-wall encoding at 100 seconds and lambda equal 0.19. This is the result, and vertical axis is energy. The energy is good if the energy is low. The horizontal axis is computation time. According to this figure, while the energy updates slow down early in the computation time for the one-hot encoding, the energy updates continue for the domain-wall encoding. Considering that fixed amplify uses simulated-annealing-based algorithm, it is suggested that domain-wall encoding will continue to update the solution even at low temperatures. This result is related to the ease of transition between integers. In one-hot encoding, the transitioning from one integer to another, they have to pass through the infeasible solution. Infeasible solution where all spins are 0. The energy barriers mu lambda between infeasible solution and feasible solution exist. Because the feasible solution difficult to transition to another integers. The field of the solutions remains trapped at local minimum. By contrast, the domainwall encodings, in domainwall encodings, the integer and neighboring integers has the same energy with no energy barriers. So, because the domainwall encoding can transition without energy barriers, it can explore without stagnating in local solutions. Finally, we investigated whether the characteristics found in the digital Ising machine could also be observed in the quantum-annealing machine. To handle the QKP in QA machine, we made a QKP. And the number of items was set to 5, and the interaction density was set to 50%. The weights and profits of the items were chosen randomly from uniform distribution on these integers. Knapsack capacity was set to 15, then the yield advantage was used as an Ising machine. Idling time was set to 20 microseconds, and penalty coefficients lambda was set to 0.1 to 0.9. Number of trials was set 100. It is the results. This figure shows it was demonstrated that even when using the QUBO advantage, that the performance of the domain wall encoding improved as lambda increased. This is conclusion. In this study, we evaluated the performance of the domain wall encoding in the digital Ising machine using QKP. This study will reveal that the performance of the domain wall encoding improved with the ratio of the penalty coefficients between the two constraint terms. Second, the penalty coefficients for the total constraint terms that obtain feasible solutions was small in the domain wall encoding. The domain wall encoding was highly sensitive to computation time. In addition, it was demonstrated that even when using the QA machine, the performance of the domain wall encoding improved with the ratio of the penalty coefficients. The data of this presentation is described in this paper, so please take a look if you're interested. Thank you for your attention.
Time for question comments.
Thank you for the interesting talk. In your results, I'm interested in the lambda depends. And in your results, when lambda equals 1, then the feasible solution rate is the highest, right?
I didn't.
In the domain wall encoding case,
In the domain wall,
the highest feasible solution rate is almost 1 when the lambda equals 1. In that case, do you mean that the constraint on the constraint term on the weight penalty doesn't need to mean? Because when lambda equals 1, the lowest one is the weight constraint become 0.
In the QKP with a large knapsack capacity, this is the result of domain wall encoding and encoding constraint and weight constraint. if the lambda is the weight constraint is always achieve the feasible solution in domainwall encoding, because maybe the in domainwall encoding the represented by the number of outside spins indicated 1, so it is easy to express, and weight capacity is large. This penalty becomes large, so the weight constraint is don't need large penalty coefficients. So weight constraints always achieve the feasible solution, and the encoding constraints is, as you know, that if the lambda is large, of course, the feasible solution rate is large. So I think that this is the number.
That's why that point is the highest. Ah, I see. Thank you. It's interesting.
Thank you very much.
Any other questions? Okay, so it's almost time. Thank you again, presenter.